According to our best model of the universe, the Milky Way should be surrounded by hundreds of small companion galaxies, orbiting us, bound by our gravity close enough, in cosmic terms, to be practically family. We've found a few dozen. Not a rounding error, not a minor discrepancy waiting on slightly better telescopes. A gap so large, so persistent, that cosmologists gave it a name decades ago and still haven't fully closed it: the missing satellite problem. And here's the part that should genuinely bother you. This isn't some obscure corner of astrophysics nobody cares about. It sits directly on top of our leading model for what the universe is actually made of. If the missing galaxies are truly missing, not hidden, not overlooked, but simply not there, it means something is wrong with how we think dark matter behaves at the smallest scales. And if they are there, hiding in plain sight all around us, it means we've been staring past 100 galaxies for decades without ever noticing them. Tonight, we're going after the ones we can't find. And we're going to ask what it means that the universe's own instruction manual keeps promising company that never shows up. Let's start with where this prediction actually comes from, because it isn't a guess. It's the output of some of the most sophisticated computer simulations ever built. For decades, cosmologists have run massive simulations designed to model how the universe assembled itself, starting from the tiny density fluctuations present just after the Big Bang and running forward billions of simulated years, tracking how gravity, and specifically dark matter, pulled matter together into galaxies. These simulations are built on our leading cosmological framework, called lambda CDM dark energy, plus cold dark matter, plus ordinary matter, all governed by gravity according to Einstein's general relativity. It's the same model that has successfully predicted the large-scale structure of the cosmic web, the afterglow of the Big Bang itself, and the overall rate of cosmic expansion with remarkable precision. When you run this model forward and simulate the formation of a galaxy roughly the size and mass of our own Milky Way, something very specific and very consistent happens. Dark matter doesn't just clump into one big galactic halo. It clumps into thousands of smaller structures too, called subhalos, miniature gravitational wells, nested inside the larger halo, each one theoretically massive enough to have pulled in gas, ignited star formation, and become a small satellite galaxy of its own, orbiting the main galaxy the same way moons orbit a planet. The simulations are remarkably consistent about the number. They predict hundreds of these subhalos, many of them substantial enough that if they collected even a modest amount of gas and formed stars, we should be able to see them quite easily in our own galactic backyard. So, astronomers went looking. And that's where the story starts to feel less like tidy science and more like a genuine, ongoing detective case. By the late 1990s, when the first detailed simulations of this kind were published, astronomers had confidently catalogued around a dozen satellite galaxies orbiting the Milky Way, objects like the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere, and known since antiquity, along with a handful of fainter dwarf spheroidal galaxies discovered through more careful, systematic survey work over the preceding decades. A dozen, against a prediction of hundreds. That's not a small gap. That's nearly 2 orders of magnitude of missing galaxies. And when the discrepancy first became clear, it landed as a genuine crisis for the model. Either the simulations were fundamentally wrong about how dark matter clumps at small scales, or hundreds of galaxies were sitting around us, completely undetected, hiding in some way nobody had yet figured out how to account for. Here's where the story takes its first, genuinely surprising turn, because it turns out both explanations were partially right, in ways nobody fully expected. Starting in the early 2000s and accelerating dramatically through the 2010s, wide-field sky surveys, projects like the Sloan Digital Sky Survey, and later, more sensitive instruments specifically designed to hunt for exactly this kind of faint object, began finding satellite galaxies that had simply never been noticed before. Not because they were hiding behind something, because they were almost unbelievably dim. These newly discovered objects, often called ultra-faint dwarf galaxies, can contain as few as a few hundred to a few thousand stars total. For comparison, our own Milky Way contains an estimated 100 to 400 billion stars. Some of these dwarf galaxies are so sparse, so faint, that they produce barely more visible light than a single bright star cluster, despite being genuine, gravitationally bound galaxies in their own right, complete with their own dark matter halos holding them together. Finding these things required an entirely different observational approach than spotting a bright, obvious galaxy like the Magellanic Clouds. Astronomers had to search for extremely subtle overdensities of individual stars, scattered thinly across large patches of sky, statistically distinguishable from the background only through careful, systematic analysis of enormous survey datasets. It's less like spotting a lit-up city from an airplane window, and more like trying to notice that a handful of scattered porch lights spread miles apart across a vast dark landscape actually belong to the same small, spread-out town. As this technique matured, the number of known Milky Way satellite galaxies climbed steadily, from roughly a dozen in the late 1990s to several dozen by the 2010s, to over 60 confirmed satellite galaxies as of recent surveys, with additional promising candidates still awaiting confirmation. That's real, significant progress. It substantially narrowed the original, alarming gap between prediction and observation. But here's the uncomfortable truth that gets left out of the more optimistic headlines. Even with every one of these newly discovered ultra-faint galaxies included, we are still meaningfully short of the numbers the simulations predict, particularly once you account for the fact that our current surveys still can't see the entire sky with equal sensitivity. That last detail matters more than it might initially sound like. Most deep, sensitive satellite galaxy surveys have focused on specific patches of sky, often chosen because the instruments doing the searching, like the Dark Energy Survey or the Panoramic Survey Telescope, have particular fields of view and operational constraints. When astronomers calculate how many satellite galaxies we'd expect to find across the entire sky, based on the density of discoveries within the smaller patches we've actually searched thoroughly, the numbers suggest there could be dozens more ultra-faint dwarf galaxies still waiting to be found, simply in regions of sky we haven't yet surveyed with sufficient depth and precision. So part of the missing satellite problem, it turns out, really was a problem of not looking hard enough, in the right way, with the right instruments. That's genuinely reassuring. In its own way, it means the model wasn't nearly as broken as it first appeared. But genuinely reassuring is not the same as fully resolved. And this is where the story gets stranger, because even accounting for observational bias, even assuming every unsurveyed patch of sky eventually reveals its fair share of hidden dwarf galaxies, there's a deeper theoretical puzzle sitting underneath the numbers, one that pure observation alone can't fully explain away. Here's the core of it. Not every dark matter subhalo predicted by the simulations should necessarily host a visible galaxy at all. And figuring out exactly why some do, and some apparently don't, has become one of the more genuinely contested frontiers in modern galactic astrophysics. The leading explanation involves something astronomers call feedback, the idea that forming stars and galaxies isn't a passive, purely gravitational process, but an active, sometimes violent one, where the earliest generations of stars and their eventual supernova explosions can blast surrounding gas out of a small dark matter halo before it ever accumulates enough material to form a substantial galaxy. In the very smallest dark matter subhalos, with the weakest gravitational grip, this feedback effect could be dramatic enough to essentially sterilize the halo, leaving behind a clump of dark matter with few or no stars at all invisible, by definition, to any telescope, because there's simply no light being produced there to detect. If this explanation holds up, and it remains an active area of both theoretical modeling and observational testing, it would mean a genuinely strange thing about our own galactic neighborhood. There could be dozens, or even hundreds, of dark matter clumps orbiting the Milky Way right now, gravitationally real, substantial in mass, doing exactly what the simulations predicted except completely dark. No stars, no light, no way to directly observe them using any telescope currently in existence, because telescopes fundamentally detect light, and these objects, if they exist as predicted, might not produce any at all. Let that settle for a second, because it's a genuinely different kind of missing than simply being too faint to notice. A dim dwarf galaxy, however faint, still has stars, however few. They still produce light, and with a sensitive enough survey, eventually, that light can be found. A completely dark subhalo, one that never forms stars at all, isn't dim. It's fundamentally invisible. In the same structural way, an isolated black hole is invisible, not a limitation of our current instruments, but potentially a limitation built directly into the physics of the object itself. So how would we ever confirm something like that actually exists if it produces no light whatsoever to detect? The answer, unsurprisingly by now, is the same indirect approach that's become the recurring theme of modern astrophysics. Gravity. If a completely dark subhalo exists, orbiting the Milky Way, it should still exert a measurable gravitational influence on anything that happens to pass near it, including, potentially, thin, extended streams of stars that have been gradually torn away from smaller satellite galaxies as they get pulled apart by the Milky Way's own gravity over billions of years. These structures, called stellar streams, form when a smaller galaxy, or a dense star cluster, drifts too close to the Milky Way and gets gradually shredded by tidal forces, leaving behind a long, thin ribbon of stars, still roughly tracing the object's original orbital path. Astronomers have identified dozens of these streams wrapping around our galaxy, and in several cases, they've noticed something genuinely strange: subtle gaps, kinks, and irregularities in the smooth, expected structure of a stream, inconsistent with the gravitational influence of anything we can currently see. Some researchers have proposed that these irregularities could be the gravitational fingerprints of exactly the kind of dark starless subhalos the missing satellite problem predicts: invisible clumps of dark matter drifting past a stellar stream, tugging it subtly out of shape as they pass, then continuing on into the darkness, undetectable by any other means. One particularly well-studied stream, called GD1, has shown irregularities that several independent research teams have specifically investigated as potential evidence of exactly this kind of unseen, dark perturbation. To be clear about where the actual science currently stands, this remains a genuinely open, actively debated area of research, not a settled conclusion. Some of these stream irregularities may eventually turn out to have more conventional explanations: the gravitational influence of already known objects, or complexities in the stream's formation that don't require any exotic dark subhalo at all. But the fact that serious astrophysicists continue investigating this specific hypothesis, using increasingly detailed data from missions like Gaia, tells you the possibility hasn't been ruled out. If anything, it's become one of the more promising indirect methods currently available for potentially confirming that some of these predicted starless dark matter clumps genuinely exist exactly where the simulation said they should be. Let's step back and consider what's actually at stake here, because this isn't merely a bookkeeping exercise about galaxy counts. It cuts directly into one of the biggest open questions in all of physics: what dark matter actually is at a fundamental level. The standard version of the lambda CDM model assumes dark matter is cold, meaning it moves slowly compared to the speed of light, and clumps together efficiently at every scale, from the largest cosmic superclusters down to the smallest galactic subhalos. This assumption has worked remarkably well at explaining the large-scale structure of the universe. But the missing satellite problem, particularly the portion of it that can't be explained away by observational bias or stellar feedback alone, has led some researchers to seriously consider whether dark matter might behave differently than the standard cold dark matter model assumes, specifically at these smaller scales. One alternative, still genuinely speculative but taken seriously in parts of the theoretical physics community, proposes that dark matter might be warm rather than cold, meaning its particles move somewhat faster, which would naturally suppress the formation of the smallest dark matter clumps in the first place, potentially explaining why there are fewer detectable satellite galaxies without requiring any exotic feedback mechanism at all. If warm dark matter turns out to be the correct description of reality, it wouldn't just resolve the missing satellite problem. It would represent a genuinely fundamental revision to our understanding of one of the universe's core ingredients, with implications reaching far beyond a simple galaxy count around the Milky Way. Nobody currently knows with confidence which explanation or combination of explanations is correct. Better observational data, larger and more sensitive sky surveys, and increasingly sophisticated simulations incorporating more realistic models of stellar feedback are all actively working to narrow down the possibilities. But as of right now, the honest scientific position is that the missing satellite problem remains only partially resolved, genuinely, meaningfully improved from where it stood decades ago, but not yet fully closed. There's something worth sitting with in that uncertainty, something that connects this specific puzzle to a much larger pattern we keep running into. Time and again, our boldest cosmological models make precise, testable predictions about what should exist around us, and time and again, reality either falls stubbornly short of those predictions, or turns out to be hiding exactly what was promised, just in a form so faint, so dark, or so quiet that it took years, sometimes decades, of increasingly clever detective work to finally catch a glimpse of it. The missing satellite problem sits precisely at that intersection. Some of the missing galaxies really were there the whole time, simply too faint for the tools of an earlier generation of astronomers to notice genuine galaxies, genuine starlight, patiently waiting for a sensitive enough survey to finally catch them. And some of what's missing may not be missing in that sense at all. It may be exactly what the models predicted, existing precisely where predicted, doing precisely what dark matter clumps of that size are supposed to do, except never accumulating enough visible material to produce a single detectable photon of light. If that's the case, then the most unsettling part of this entire story isn't that we've been slow to find these galaxies. It's that some of them may never be found, not through any failure of effort or technology, but because they were never going to be visible in the first place. Dark by nature, rather than dark by circumstance. So here's the truth we're left with tonight. The Milky Way is supposed to be surrounded by hundreds of companion galaxies, according to some of the most rigorously tested cosmological simulations ever built. We've confirmed a few dozen bright ones, known since before we understood what they truly were, and several dozen more faint ones, discovered only in the past 2 decades through painstaking, systematic searches of the night sky. And somewhere in the gap that remains the still uncounted difference between prediction and confirmed observation, there may be a genuine mixture of 2 very different kinds of missing galaxies simply too faint for our current surveys to have reached yet, and galaxies that were never going to shine at all, drifting silently around us as pure, starless dark matter, detectable only through the subtle way they tug at the stars unlucky enough to pass close by. We are, right now, orbited by 100 unanswered questions, each one potentially massive enough to be its own galaxy, hiding in the dark spaces between the ones we've already found. Some of them are waiting for a better telescope. Some of them, if the theory holds, are waiting for nothing at all, because there was never going to be any light for us to eventually catch. The next time you look up at the night sky, remember that the galaxy you're standing in is supposed to have company. Dozens of unconfirmed companions, and possibly dozens more that will never produce so much as a single photon for us to find. They're out there right now, tracing quiet orbits around the same galactic center as our own sun, closer to home than almost anything else we study in astronomy, and still, somehow, among the hardest things in the entire universe for us to actually see.